So today I'm going to talk about this paper called the Stereographic Markov chain Monte Carlo. So it's not a very new paper. It has been on arXiv at least 2.5 years. But it's one of my favorite papers. So this is joint work with Chris and Gareth. So both are from University of Warwick in the UK. So give a brief review of what is Markov chain Monte Carlo. So the idea of Markov chain Monte Carlo is very simple. So we want to construct a Markov chain. So the stationary distribution of this Markov chain is designed to be a target distribution that you want to get a sample from. So we run this Markov chain starting from some initial state for some number of iterations. So we know under certain condition, this Markov chain will converge to the stationary distribution. Then we can use the output of this algorithm as approximate samples of your target distribution. So basically, that's the idea of MCMC algorithms. So when we run a Markov chain Monte Carlo algorithm, there are roughly two phases. So in the first phase, we start the Markov chain from some initial state and we run it for a certain number of iterations. And what we hope is after this number of iteration, this Markov chain has converged close enough to the stationary distribution. So the first period is called the transient phase or burn-in. So maybe the most important question to ask is to ask how many iterations we need to run. So that's corresponding to the mixing time of a Markov chain. But after this burn-in period, the second phase is called the stationary phase. So in this stationary phase, we want to use the samples, like the output of MCMC algorithms, to do Monte Carlo estimation. Then the key question to ask is about the quality of the samples produced by this MCMC algorithm. It corresponds to how efficiently this Markov chain can explore the state space. In the stationary phase, we can study, for example, the autocorrelation function of the output of this algorithm, or we can study some a notion of effective sample size or ESS. So basically, the idea of effective sample size is to say how good the sample compare with independent samples, because MCMC algorithm almost always produce positive correlated samples, which means you need to simulate more samples in order to get a certain number of ID samples, like equivalent to a certain number of ID samples for the Monte Carlo estimation. And in this talk, we also will mention this expected square jumping distance. So this is corresponding to a theory called the optimal scaling. So basically, the idea is in the stationary phase, if the MCMC algorithm on average jump a large distance, it's a good sign because it means the sample produced by this algorithm tend to have a smaller correlation, which means the quality of the sample is good. My research is basically focused on the high dimensional Markov chain Monte Carlo. And the reason is MCMC is widely used for sampling like a posterior distribution in Bayesian inference. And this in Bayesian inference, the dimension of the posterior distribution usually is the same as the number of parameters in the statistical model. So you can imagine, so nowadays in modern Bayesian statistics, people tend to use very complicated models, which means the number of parameters is huge. So if you want to sample the posterior is in a very high dimension state space. So this high dimensional setting really bring new challenges and opportunities. For example, in the transient phase, we may want to study the mixing time of Markov chain, how it scales with the dimension of the state space. If, for example, the mixing time increase exponentially fast with the dimension, then we say this MCMC algorithm doesn't scale well to high dimensions. And similarly, in stationary phase, we also can study, for example, how this autocorrelation function behaves when the dimension increase, or how the effective sample size decrease with the dimension, right? So in this talk, I will basically introduce a new framework of designing new MCMC algorithm that can have a good performance in high dimensions. So the outline of this talk is as follows. So at the very beginning, I will give a review of two existing MCMC algorithms. So the first algorithm is called random walk Metropolis. So this is a very simple construction of a discrete time reversible Markov chain, which has the target distribution as the stationary distribution. And the second algorithm is called the Bouncy Particle Sampler, or BPS. So this is a construction of a continuous time Markov process and also a non-reversible Markov process. And after review of these two algorithms, I will mention two issues. So the first one is if the target distribution has a heavy tail. Then I will explain why these two algorithms, none of them is geometrically ergodic. So geometric ergodicity is a property of a Markov chain. That usually we hope our MCMC algorithm is geometric ergodic because geometric ergodicity implies a Markov chain central limit theorem. Once we have a Markov chain central limit theorem, we can collect the samples from MCMC algorithm and do a certain type of inference using the samples. So unfortunately, you can see if your target distribution has a heavy tail, none of these two algorithms is geometrically ergodic. So the second issue I will mention is high dimension. So I will explain why the mixing time of this algorithm increase with the dimension D. And after this two algorithms and these two issues, I will introduce two new algorithms. They call Stereographic Projection Sampler, SPS, and the Stereographic Bouncy Particle Sampler, SBPS. And then I will go back to these two issues again. So for the first issue, for heavy tail target, I will show the two new algorithms. They can be uniformly ergodic for even heavy tail targets. And the second issue in high dimension, I will show in the best scenario, the mixing time of these two new algorithms can even decrease with the dimension D. Okay, so let's start from the first very simple Markov chain called the random walk Metropolis algorithm. So it's a very simple construction. So imagine the current state of the Markov chain is at a small x. Then I will first do is a random walk proposal. Then I will compute the proposal basically centered at the current location of the Markov chain and by a random walk, that's Gaussian random walk, with only one tuning parameter, that's the proposal variance. And after that, it's a Metropolis Hastings framework. So I will decide to accept this proposal with a probability like this. And if the proposal is accepted, this Markov chain move to the proposed state Y. Otherwise, the Markov chain stay at the current state X. So you can imagine that if my target distribution pi has some smoothness density, then if this proposal is proposal variance is very small, then this proposal y is very close to x. Then this ratio is very close to 1. Then the proposal is very likely to be accepted. However, if this proposal variance is very big, then y can be very far away from x, for example, at the tail region. Then the density ratio is very close to 0, then the proposal will be very likely to be rejected. So here's the picture for the basically the behavior of the Markov chain. If the proposal variance is too large, you can see the Markov chain stuck at one location for a long time and then suddenly has a very large move. And if the proposal variance is too small, you can see the Markov chain keep moving in the state space. However, it's not very efficient because the move is very small. So there's an optimal proposal variance that the Markov chain explore the state space most efficiently. So this problem is already studied by a theory called optimal scaling. For example, we can maximize this tuning parameter proposal variance or proposal step size h by maximizing the expected square jumping distance of the Markov chain. So the result from optimal scaling basis suggests this proposal step size should decrease with the dimension with this order 1 over square root of d. And also the optimal acceptance rate for the this algorithm random walk Metropolis roughly 23%. So this number 23% is very useful because in practice, if you use this random walk Metropolis, you just need to tune this tuning parameter to roughly get 23% proposal accepted. However, in this talk, this number is not very important for us. So the important message is the proposal step size should decrease with dimension roughly with this order 1 over square root of d. Okay. And the second algorithm it's called the Bouncy Particle Sampler. So it's a very new, relatively new algorithm. It belongs to a family called the piecewise deterministic Markov process, or PDMP. So PDMP is now the focus of this talk. So I will give a very brief introduction of this algorithm using a Gaussian target. So if we look at this picture on the left-hand side, so the color represent this two-dimension standard Gaussian, the density. So the yellow color region is the high probability density region, and the blue color is corresponding to the tail region. So because this algorithm is a continuous time algorithm, you can just imagine there's a particle in the state space and keep moving in continuous time in the state space. So imagine there's an initial state location for the particle called x0. And we also have an initial velocity. So in this talk, I will only consider unit speed. So this basically the velocity is about the direction. So with the initial location and the initial direction, then these two uniquely determine a straight line in the state space. So the particle just move along this straight line with unit speed until one of the two types of events occur. So the first type of event is called the bounce event. So when the bounce event occurred, this particle changes the direction, and how it changes the direction depends on the contour line of the target density at the location, and do basic Newtonian elastic collision. It's like a reflection, so it bounces back. So you can see the first bounce event occur at here. So the particle changes the direction basically by reflection according to the contour line and this location. And after that, this new direction together with the new location also determine another straight line. So the particle continue move along this straight line with unit speed. So you can see from this picture, there's a second bounce event occurred at this location. So the particle bounce again. And the third event is the second type of event called refreshment event. So in this refreshment event, if this refreshment occurred, then the particle changes the location by a random direction. Okay, so how we simulate this bounce event and the refreshment event? So the bounce event is simulated using arrival timers of inhomogeneous person process, where the intensity of this person process is using the gradient information along this path. So this bounce events really guarantee if the particle in this example trying to leave this yellow color region, then there will be very likely a bounce event occurred. So make sure that this particle with high probability will stay in this yellow color region, which is high probability density region. So you can see for the second event, also the particle try to go to the yellow, try to leave the yellow color region, go to the tail region, then the second bounce event occurred. Okay. However, if we just simulate this bounce event, there's a problem. You can look at the picture on the right-hand side. This is for the standard two-dimension Gaussian if we just simulate the bounce events. So this problem is this particle will never be able to visit the area inside just by bouncing. So that's the reason we have to introduce another event called refreshment. So this refreshment event basically we simulate arrival times of a homogeneous person process with a constant like a parameter, which is another new tuning parameter. So just to make sure this Markov process is ergodic. So that's the basic reason. Okay, so this is basically the algorithm. You can see the bounce event really use the gradient information of your target distribution. So in some sense, this is the efficient events. You kind of want to simulate more bounce events, but the refreshment event is have certain random walk type of behavior. So you kind of want to try to simulate less refreshment events if possible. So basically, these are the two algorithms, random walk Metropolis and the Bouncy Particle Sampler. So let's look at the first issue when the target has a heavy tail. So if your target distribution has a heavy tail, by definition, that means the tail is heavier than the exponential tail. For example, for multivariate student T distribution with any degree of freedom, that's a heavy tail distribution. So before I introduce the result, I will show you this, what's the definition of a geometric ergodicity. So roughly speaking, if a Markov chain is geometrically ergodic, then starting from some initial distribution x after k iteration, then the distribution of the sample is close to the stationary distribution in total variation distance, upper bounded by this bound. So there's a constant m which depends on the initial state, and also a constant rho to the power k. So rho is smaller than 1. So you can see this, if a Markov chain is geometric ergodicity, geometrically ergodic, then for any given initial state, this total variation distance to the stationary distribution decay exponentially fast. However, this constant m of x depends on the initial state. So you can have a arbitrarily bad initial state. So this m of x can be arbitrarily large. So in that sense, in practice, the convergence can still be very slow. So what is uniform ergodicity? So if a Markov chain satisfies uniform ergodicity, then this constant m doesn't depend on x. So it can be bounded by like one constant m for any initial state x. So unfortunately, for general MCMC algorithms such as Metropolis Hastings algorithm, if the state space is Euclidean space, which is not bounded, so usually uniform ergodicity doesn't hold. So the best you can expect is the Markov chain Monte Carlo algorithm is a geometric ergodic. However, if the state space is bounded, usually we can establish uniform ergodicity. Okay. So let's have a look at these two algorithms we just mentioned. So for heavy tail target, what's their property? So for the first algorithm, random walk Metropolis, so random walk Metropolis is never geometrically ergodic for any heavy tail target. And also random walk Metropolis is never uniformly ergodic if the support of the target distribution is Euclidean space. For the Bouncy Particle Sampler, we have a similar result. So Bouncy Particle Sampler with unit speed is never geometrically ergodic for any heavy tail target. So we don't have this uniform ergodicity result, but I believe a similar condition for this random walk Metropolis also hold for Bouncy Particle Sampler. So you can see if your target has a heavy tail distribution, then you never get a geometric ergodicity for these two algorithms. So let's go to the second issue, which is high dimensional settings. So before I show you the results for these two algorithms, let me emphasize. So MCMC in high dimension, because the target, the posterior distribution, usually have some concentration phenomenon, which is kind of like a counterintuitive. It usually connects to some surprising facts about high dimensional geometry. So in this talk, I will use the simplest possible high dimensional target you can imagine, which is the standard Gaussian target, but in high dimension. So if I want to imagine, I want to sample, it's a toy example. I want to sample one-dimensional Gaussian or two-dimensional Gaussian. I want to simulate a Markov chain for sampling this target. So what's the best behavior for this Markov chain? So you can imagine the Markov chain can start from initial state, which is very far away. But the best behavior for the Markov chain is, first of all, it should go to the neighborhood of the mode of this Gaussian as fast as possible. This is roughly corresponds to the transient phase or Berlin. And after it arrives at the neighborhood of the mode, it should stay around this neighborhood of the mode with high probability. That this is roughly corresponding to the stationary phase of the target. However, this intuition doesn't hold in high dimension. For example, if we have a target which is the standard multivariate Gaussian, but with a very high dimension D, so if we got a sample from this target, you can easily verify the square norm of this sample can be written as a sum of each coordinate square, and each coordinate square is independent chi-square random variable with degree of freedom 1. Then by law of large number, this square norm will converge to the mean, which is equals D, and has a standard deviation square root of D. Which means if you have a random sample from standard Gaussian, this random sample actually is not in the neighborhood of the mode. actually it's quite far away from the mode because the square norm is almost equals d, which means the distance to the mode is almost square root of d. Right, so if you want to design a Markov chain sample this high dimensional Gaussian target, then the bicep behavior should be like this. So the Markov chain can start from a very far away, but it should go to a distance to roughly square root of d to the mode as fast as possible. And this roughly corresponding to the transient phase. And after that, this Markov chain should stay around this distance roughly equals square root of d to the mode and explore the shell like all this area, because that's the area that most of the density of a Gaussian target concentrated on. So you can see the intuition is very different. So in summary, this sample from a high dimension Gaussian takes values very close to a shell, roughly radius square root of d. With the center is the mode of the target. And the mixing time of this Markov chain roughly corresponding to the time of arrival at this shell. Okay. Then let's just run this random walk Metropolis for this target. So the simplest target you can imagine, the high dimension Gaussian target. So what I did is I ran this random walk Metropolis in 100 dimension. And the initial state for this random walk Metropolis at one point that all this coordinates in 100 dimension equals 20. And this what I plotted is the first two coordinate was the path of this Markov chain. So you can see the Markov chain start from here. And there's a small red circle here. I don't know if you can see it. It roughly corresponding to the marginal, the first two-dimension marginal Gaussian. So at least in the transient phase, the goal for this Markov chain is to move from this point to this circle. Right, so you can see what the actual behavior for this random walk Metropolis. It seems to have a very hard time to find where to go. So what's the direction to go? So it spent a lot of time doing this random walk behavior at the tail before it can find the direction to go to the circle. So why this happens, right? So I can explain this by a very simple like argument. I will use this argument many times in this talk. So imagine the current Markov chain is here. So I will propose a random walk proposal, right, from here. So however, you can imagine the direction you want to go is you can draw one line from this direction to this circle. So that particular direction is really the direction I want to go. But this is in high dimension, 100 dimension. So there's one particular dimension pointing to that circle. That's the correct direction. And then they have a 99 dimensional subspace, which are orthogonal to this direction. And any move in that orthogonal direction won't help, right? But it's a random walk proposal, which means by law of large number, most of the component by this random walk is working in the orthogonal space. So most of the component of this random walk is in the orthogonal space. But if you move in the orthogonal space, a very large move, then by the curvature, actually you are leaving the circle. Right, so in order to not to the proposal not to be rejected, so you have to choose a very small step size, but to kind of balance these two. One direction is a correct move, but very small. But most of the move in orthogonal space, you have to take a very small step size. So in that sense, you have a d-1 dimensional subspace are orthogonal. So you can see the squared like proposal, this square distance is a basic chi-square with a degree from d-1, which dominate that particular move in that one dimension. So as a result, you have to choose the subsize h to decrease with dimension with exactly this order, basically obtained by the optimal scaling theory, right? In order to make sure the optimal, so the acceptance rate doesn't go to 0. So that's basically the behavior for this random walk Metropolis. So you can see that the problem is this random walk proposal is very inefficient in the high dimensions. So let's look at the Bouncy Particle Sampler. So as I said, the bouncy particle sampler, you have to rely on this refreshment events in order to explore some space. For example, for this Gaussian, you want to go inside. On the picture on the right-hand side, you can see the particle has had a reflection event here, so it moves inside, right? So you have to rely on this. So I can use the same argument if in high dimension. You have to rely on basically random direction to go to a particular direction. But once you have a refreshment event, you generate a random direction. So the random direction basically has a very small component going to the right direction. And the most of the components are actually in the orthogonal space. So you have the same issue. So which means the refreshment is very inefficient in the sense that most of the refreshed direction, most of the components are orthogonal to the direction you really want the Markov chain to go. So as a result, in high dimension, you may have to simulate a large number of refreshment events in order to make the Markov chain goes to the direction you want to go. However, as I said, the refreshment event is kind of not using the gradient information of your target, so it's a kind of random walk behavior. So you still have the problem. The BPS won't be very efficient in high dimension. Okay, so now let's go back to the new idea. So this new idea by this paper basically use a very simple idea. So the idea is in order, like instead of designing MCMC algorithm in the Euclidean space, we do a simple variable transformation. That's we transform this Euclidean space to a compact set. In this picture, it's a high dimensional sphere. And then we basically design a Markov chain running on the sphere to sample a transform target. And then we can transform back to the Euclidean space. Then we automatically get the Markov chain Monte Carlo algorithm sample the original target distribution. So basically that's the idea. So from this picture, you can see this is called the classical stereographic projection. So you can imagine this is a sphere I put on the Euclidean space, right? And then for any point in the Euclidean space, I can draw a straight line from the north pole of the sphere to this point on the in the Euclidean space. And it will intersect this sphere with only one point. And then I will just map this point in the Euclidean space to this point on the sphere. And similarly, for any point on the sphere except the north pole, I can do the same. I can know how I can map this one point on the sphere to this point in the Euclidean space. So you can see this is almost a one-to-one mapping between Euclidean space to the sphere. So the only exception is the point north pole, which is not a map to any point in the Euclidean space. So I will just simply add one state to my state space called the infinity, and I will map the north pole to this infinity. So in that sense, I have a one-to-one mapping. Okay, so I will do is just introduce a new algorithm by this simple idea I just described. So this first algorithm is called the Stereographic Projection Sampler. So this is really just a random walk Metropolis algorithm. So imagine my current Markov chain, the location as small x in the Euclidean space. Then I will propose a random walk proposal. However, I won't propose the random walk proposal in the Euclidean space. So what I will do, I will first use the stereographic projection to project this point in the Euclidean space called small x to one point on the sphere. So it's called Z. And you can see the picture, the current location after transformation of the Markov chain is at this point Z. Then I will do a random walk proposal in the tangent space. So in the tangent space at this point Z, I will generate a Gaussian with a proposal variance h square. And then after this random walk, this Markov chain move to this blue color point called Z plus dz. However, because it's moving in the tangent space, this blue color point is outside of the sphere. So I will simply do a renormalization to renormalize it. So back to sphere is called Z hat. So you can imagine this is perhaps the most naive way of simulating a random walk a proposal on the sphere. So this point Z hat is my proposal on the sphere. Then I will do I will use the Stereographic projection to map this that had back to Euclidean space. And this is my proposal in the Euclidean space. That's my proposal Y. So you can see the only difference is the transformation. It's the simplest random walk proposal. So then I will, as a Metropolis Hastings step, I will accept this proposal with some probability. So you can see the only difference is there's a ratio here. It's basically the Jacobian of the transformation. And then I have introduced another tuning parameter called capital R here. So it basically the radius of the sphere. So in this picture, I'm basically use the unit sphere. So the radius is always 1. But before I project it back to Euclidean space, I will choose the radius. I will enlarge the sphere. So the radius equals capital R, which is another tuning parameter. Then I will use the stereographic projection to project it to Euclidean space. So you can see this algorithm only have 2 tuning parameters. One is proposal variance or proposal step size on the unit sphere, and then I have a radius of the sphere. Okay, so this is the first algorithm. And the second algorithm is called the Stereographic Bouncy Particle Sampler. So basically, it's the same idea. So I want to implement Bouncy Particle Sampler on the sphere. So the basic idea is very simple. So the traditional Euclidean version of Bouncy Particle Sampler, the particle move in Euclidean space along straight line with unit speed. So now I will let the particle move along greatest circle on the sphere with unit speed. Because any like a location of the particle on the sphere with a direction in the tangent space uniquely determine a greatest circle. So the particle just move along this greatest circle with unit speed. And at certain random time, I can simulate a bouncing event or a refreshment event occur. So I will do the same. If a bouncing event occur, I will do the reflection according to the target density at this tangent space at the current location. And if a refreshment event occurred, I would refresh the velocity direction in the tangent space. So that's basically the same idea. So you can imagine once I simulate this bouncy particle sampler on the sphere, I can use stereographic projection to project it back to the Euclidean space. So I automatically get some trajectory like this. So you can see this is on the left-hand side is if I simulate SBPS without refreshment for the 2-dimensional Gaussian target. So you can see there's some observation. First of all, this SBPS is still a piecewise deterministic Markov process because each piece become an arc. Right. However, this SBPS in the Euclidean space is not a unit speed because we simulate this BPS on the sphere with unit speed. But after you project back to Euclidean space, actually this particle automatically speed up at the tail and slow down in the center. Okay, so it's not the unit speed anymore. And furthermore, we still have this ergodicity issues, right? So if we don't simulate this refreshment event, this particle won't be able to visit any area inside. So we have to simulate the refreshment event to get this trajectory like the picture on the right-hand side. However, later I will explain why this refreshment event is very efficient in the high dimensions. Okay, so that basically the 2 new algorithms. So let's go back to these 2 issues that I mentioned before. So the first one is how about my target has a heavy tail. Okay, so if you think about this stereographic projection, it basically map all the tail region to the neighborhood of a North Pole or Arctic Circle. So if the Markov chain you construct on the sphere can kind of escape this Arctic Circle very fast, then the Markov chain in the Euclidean space can escape like speed up at the tail very fast. So as a result, we can use the compactness of the sphere to show that this 2 new algorithms, they can be uniformly ergodic for heavy tail distribution. So the first theorem is about this first algorithm, SPS. So we can show this SPS is uniformly ergodic if and only if this condition holds. So basically you can ignore this R square. So it's really about the tail condition. For example, this condition satisfies if the target is a multivariate student T with a degree of freedom larger or equal to D. So this condition is optimal in that sense. If this condition doesn't hold, then SPS is not even geometrically ergodic. And the second result for SBPS, we have a result that this SPPS is uniformly ergodic if this condition holds. It's also a tail condition. It has a satisfied, for example, for a multivariate student T distribution with degree of freedom slightly smaller, D minus half. So this condition, our conjecture is not optimal. Our conjecture is that the optimal condition is the degree of freedom larger or equal to D minus 1, which is this condition is on the right hand side is smaller than 1 instead of smaller than half. So there will be half a degree of freedom gap. I want to emphasize these two results are based on we are using the standard stereographic projection to do the transformation. So in the ongoing work, we basically study if we can use some slightly different transformation, then actually the condition can be improved. Basically, this degree of freedom can, the lower bound can become 1. That's basically corresponding to the Cauchy tail. So basically, if you can use a slightly different transformation than stereographic projection, the standard stereographic projection, then you can get the uniform ergodicity for free if your target is has a tail lighter than Cauchy tail. I will mention in the last slides about ongoing work. Okay, so this is a toy example in the paper. So basically, it's a realistic example as a Bayesian like a Cauchy regression. So basically, we assume the data we observe come from a Cauchy distribution with some parameters. Alpha is the intercept, and the beta is a vector which correspond to the slope, and this is scale parameter gamma. So under certain setting, then we can have a posterior distribution for this alpha, beta, and gamma. And then we do a log transform for this gamma. And then we can run, for example, random walk Metropolis for this particular posterior. So the posterior for alpha and beta actually is a heavy tail. And we can also run this SPS for this posterior. And so you can see the result. This SPS converge very fast. If you look at this two-dimension picture, which is the first coordinate is alpha, and the second coordinate is the first coordinate of the slope. So this SPS converge very fast. However, this random walk Metropolis basically did this diffusive behavior at the tail. It seems it has a very hard time to find where to go. So because this posterior is a heavy tail target, and then this random walk Metropolis is now the geometric ergodic. Okay, so now let's go to the second issue in high dimensional settings. So before I show you the simulation for our algorithm in high dimension, so let me emphasize. So we always have some intuitions about a 3-dimensional ball or 2-dimensional sphere. However, those intuitions can be very misleading in high dimensions. And in this slide, I will show you some fact about how high dimensional geometry with the property of a high dimensional sphere or high dimensional ball. So imagine you have a unit ball that's in D dimension. D is very large. Right, so the first fact is this volume of this high dimensional ball is almost 0. So actually, this the volume of this ball is take a maximum as a dimension equals 5, and then after you increase the dimension further, the volume decreases, and it decreases really fast. If you look at this approximation, there's a power term d, but also in the denominator there's also a d. So it's a decrease even faster than exponential rate. So that's the first fact. And the second fact is almost all the volume of a high dimensional ball is concentrated near the boundary sphere, which means if you consider the high dimensional ball is kind of orange or apple, and then you peel this orange or apple, then there's nothing left. Okay, and the last fact is perhaps even more surprising. Is almost all the volume of this high dimensional ball lies near its equator. The reason is perhaps more surprising is you can define equator in many ways you like. For example, you can name any point on the sphere to be the North Pole, and just name the point at opposite to be the South Pole. Then you can have an equator, basically the older point in the middle. right? And then you can define the equator anyways like this. But the fact is almost all the volume of this high dimensional ball lies at the equator, any equator defined you like. So you can see this intuition about high dimensional sphere or high dimensional ball is very different. So later in my talk, I will use one property. This property basically you can basically imagine from all these facts. So I will the fact is suppose my Markov chain start from the North Pole, and I will do a basically random walk with a constant step size. But my goal for this random walk is to starting from the North Pole, but arrive at the equator. And the fact is the number of walks I need actually decrease with the dimension. So this will be the property I will use later, and I will have a one line proof for this fact. Okay, so now let's look at this performance for SPS and also for this simplest target Gaussian, but in high dimension. So if you remember at the beginning of the talk, I explained this concentration region for this Gaussian target, concentrate to a shell with a radius roughly square root of d, right? And then you can just imagine in this picture, this circle is that shell with a square root of d like a radius. Then I also mentioned that if I want to sample a design Markov chain, sample this Gaussian target, the best behavior should be the Markov chain starting from very far away, should go to the shell as fast as possible. And after that, it should stay around the shell. So basically explore the shell. But if for this stereographic projection sampler, I put this sphere exactly like this picture, then basically I map all the concentration region that shell to a neighborhood of this equator. Then equivalently, I want to design a Markov chain on the sphere, maybe start from a very far away, like very close to the North Pole. But it goes to the equator as fast as possible. And then after that, it stay around the equator, start to explore the area near the equator. That will be my best Markov chain to sample this target, right? And then I will show this SPS algorithm satisfy these two properties, which means in the transient phase, is about the mixing time is roughly the number of steps from the North Pole to the equator. And I will show it actually decrease with the dimension. And in the stationary phase, once this SPS already arrive at the neighborhood of the equator, you can choose a very large proposal variance, and this SPS will stay around this equator with very high probability, which means it's only explore the neighborhood of the equator with very high probability. That satisfies both property for the best behavior for the Markov chain to sample this target. So how I can show this? So basically, I use this one line. So because this Gaussian target is anisotropic target, so I only need to focus on the latitude, right? So the latitude in this formulation is the last coordinate of this z, which is the d+1 coordinate of this z. So I can just look at the proposal latitude, which is on the left-hand side. That's the last coordinate of this z hat, as a function of this current latitude, which is the last coordinate of this z. Okay, you can see on the right-hand side, if I look at, so there's a capital U here. Capital U is one-dimensional standard Gaussian. And there's a H, which is the random walk proposal step size. Let's consider this step size is a constant now. So you can look at the right-hand side in the square bracket. There's no dimension D, right? For given current latitude, so H is the step size is a constant, and U is a standard one-dimensional Gaussian. So there's no dimension D appear in this term in the square bracket. So the dimension D only appear in this factor. So you can see for given current latitude, if I increase the dimension, so the proposal latitude will decrease, which means in the transient phase, this Markov chain will move to the equator faster in higher dimension. So in the stationary phase, imagine this latitude is close to 0, which is corresponding to the equator. So you can just ignore this term. And then the proposal latitude roughly is a Gaussian. right? Because this capital U is Gaussian, and divided by this term. However, there's a h here. You can choose this h arbitrarily large, because it will cancel with this denominator square root of h square. Which means that you choose h arbitrarily large, this proposal latitude is still Gaussian with roughly 1 over square root of d standard deviation. Which means the proposal latitude very high probability is still very close to the equator. Right? Which means in the stationary phase, you can choose arbitrary large variance and it will keep exploring this neighborhood of the equator. So how to prove this one line? Actually, it's very simple to prove. So because we want to study the latitude of this z hat, it comes from this blue color point. And the blue color point comes from this random walk in the tangent space from z. So we can just think about what's the latitude of this blue color point. Because it comes from this random walk in the tangent space, I can use the argument previously I used again. So it only have one direction. I can decompose this tangent space move into one direction, which is exactly this direction. Any move in this direction directly change the latitude. And also d minus 1 orthogonal space, which is basically subspace pointing outside the screen, if you can imagine. That's d minus 1 orthogonal subspace. Any move in that orthogonal space won't change the latitude. So which basically means the latitude of this blue color point only determined by one particular marginal Gaussian in the tangent space. So that's basically my capital U here. Right? And after this move, this latitude of this blue color point basically can be approximated by the term in the square bracket. So it doesn't depend on the dimension, it only depends on one particular marginal Gaussian. However, this blue color point is outside of the sphere. So I need to renormalize it based on the norm of this blue color point. So this factor base is 1 over the norm. So you can see the norm is the only factor that the dimension show up, because the orthogonal move in the orthogonal space, which won't directly change the latitude, is a very large move because that's a d minus 1 dimension move. So roughly, it has a move h square multiplied by a chi-square random variable with d minus 1 dimension, the degree of freedom. So what I did is just replace the chi-square random variable by the mean of it. So that's an older approximation I did. Right, so you can see that's basically the proof. So let's look at this performance of this SPS for sampling this high dimensional Gaussian target. So in this picture, if you look at the first column, that's the performance of this SPS. So this is the trace plot for the first coordinate and autocorrelation function of it, and the negative log target density and its autocorrelation function, and also the first two coordinates. And the other three columns are the performance for random walk Metropolis, starting from different coordinate, different initial state. Basically, that's they start from all the point all the coordinate equals 10, 20, or 50. So you can see from this performance, the random walk Metropolis really relies on the initial state. For example, if you start this random walk Metropolis from very far away after 5,000 iteration, you haven't seen this Markov chain from this picture. And from the autocorrelation function, you can see it produces highly correlated, positive correlated samples. However, for the SPS, you can see the samples are almost uncorrelated samples, right? And then you won't even see the transient phase of this Markov chain, because the mixing time even decreases with dimension in this case. So let's look at the second algorithm, which is the Bouncy Particle Sampler version. So I can use a similar argument, right? So I can still, I just need to argue this. Once you have a refreshment event, it actually helps the particle moving to the equator, right? So because the concentration region of the target already mapped to the equator, so in the transient phase, if there's a refreshment event occurred, let's say the particle is near the equator, for example, and then you refresh the velocity direction. And the new direction in the tangent space at the North Pole uniquely determine a greatest circle, but any greatest circle will pointing to the equator. So if the particle walk along that gradient circle, any of the direction, it will finally arrive at the equator. So any of the direction points to the equator. And in the stationary phase, if the particle already near the equator and there's a refreshment event occur, then I will argue this new direction won't make the particle leaving the equator with very high probability. The reason is I can use the same argument again. If the particle currently at the equator and there's a refreshed direction, I can decompose this tangent space into one particular direction that's basically pointing either to the North Pole or to the South Pole. And all this orthogonal d-1 direction, they are orthogonal to that particular direction. So most of the component of this refresh velocity will be in that orthogonal space. And the orthogonal space make the particle stay in the equator, because the equator actually is a d-1 dimensional sphere. Which means if you have a refresh imbalance, actually it won't make the particle leaving the equator, then you can just simulate a very small number of refreshment event, and you can simulate more bounce event. So let's look at the performance of this algorithm. So I should stop in 5 minutes, right? Okay. So let's have a look at this algorithm. So let's be quick. So if you look at the autocorrelation function for this algorithm, so there's some interesting observation. So the autocorrelation function doesn't look like a typical autocorrelation function from MCMC algorithm, because it has some periodic behavior, and also the autocorrelation function can even take negative values. So if you look at the effective sample size for each event I simulated, for the first two examples, actually it can be larger than 1. And the reason is really because the samples I simulated from this stereographic Bouncy particle sampler has a negative correlation. So you know if you have a Monte Carlo algorithm give you negative correlated samples, if you use it for Monte Carlo estimation, actually it converts even faster, which means the effective sample size can even larger than 1. Okay, so I will go quickly the optimal scaling result. Perhaps I will skip this result. I briefly talk about what the result looks like. So we also have this directly comparison of these two algorithms, stereographic bouncy projection sampler with Euclidean version random walk Metropolis. And we can establish the maximum expected square jumping distance for two algorithms for the same class of distribution and directly compare them. So we can just compare this ratio. If the ratio is larger than 1, means SPS is more efficient than random walk Metropolis. And we can show this ratio actually equals 1 divided by 1 minus alpha times beta times gamma. So this alpha, beta, gamma are constant. They are from 0 to 1. So you can imagine if alpha, beta, gamma, one of them equals 0, then these two algorithms kind of become the same. But if all this alpha, beta, gamma is very close to 1, then this ratio can be arbitrarily larger than 1. So this is algorithm can. So this theory, this theorem basically it can be considered as a robustness result and can also give a guidance for adaptive MCMC. So what is the best performance? For alpha is a penalty for misspecified radius. Means if you don't choose the radius optimal, then you suffer a constant alpha. And this beta equals to some variance divided by second moment. So we know this equals 1 if the mean is 0, which means you should have a target has a mean 0, or equivalently, you should locate this sphere to the mean of your target. And finally, this gamma is a distribution specific penalty. Basically, it's a measure how your target distribution is close to an anisotropic distribution. For example, Gaussian is an anisotropic distribution, so this gamma equals 1. Okay, so basically this is the theorem. So in the last 3 minutes, perhaps I just show you this final slide. That's selected ongoing work up to this month I'm aware of. I only listed the junior author of all this work, and many of this work are not like a joint work with me. So I want to emphasize we have a follow-up paper, which is a robust gradient-based MCMC algorithm. So if you find this talk interesting, there's an online video. I think there will be an online video in this link, because last week there was a workshop at Newton Institute in Cambridge. So my talk is recorded and it will be online. If you click this link after maybe 2 weeks, you perhaps will see the video. And for more theory and the method, let me emphasize this, the first two work. So the first work, joint work with Sebastiano. So we study, change the stereographic projection to a slightly slightly different version. Then we can fit Cauchy up to Cauchy tail. We can get the uniform ergodicity, and we can also adapt skewness of the target. And for the second work, joint work with Federica, so we study convergence complexity, basically the mixing time upper bound for this SPS, and we can show the result for a much larger family of distribution, including heavy tail distribution, which really go beyond the log concavity regime. So I also have listed other people's work, so you can have a look. So that's basically everything for today. Thank you.